So one of the important ideas here we're working with radicals is simplifying them. Here's a very useful theorem to simplify them. If you have two numbers, right, A and B, and one of them, at least one of them is positive. Maybe they could both be positive, but I want at least one of them to be positive. If that's the case, then you can break this up into little baby radicals, so long as this is a product. Something times something, well, you can break it up into the square root of something and the square root of something. Radical of the product, that's the radical of the product of two things, is the same thing as the product of the two radicals. Again, the radical of a product is the product of the radicals. That's why it's called this. Radical of the product is product of the radicals. In other words, you can break up the radical into little baby pieces. Here, talk is cheap. Let's actually do it so you can see what we mean. So suppose you have the square root of 12, for example. What you could do with the square root of 12, you can say, well, this would be the square root of 4 times 3. That's just times table. Times table says 4 times 3 is 12. Now this one says that if one of them is positive, well, one of them positive, yeah, actually they're both positive. I can break this up into little baby radicals. Radical of the product is product of the radicals. But wait, there's more. If I do that, being that the square root of 4 is evenly found to be 2, because 2 times 2 is 4, I can simplify it that way by definition of radical. And what I've done is this process here is called simplifying the radical. Sometimes it's useful, sometimes whatever, but it's really important to know, I think. Sometimes it's overplayed, but I think it's still really important to practice. Let's practice it some more. Here, what about the square root of 20? Well, I could say, well, that's the square root of 4 times 5. That's by times table. See, anytime that the 4 goes into it, you can break it up into little baby pieces because you know the square root of 4 is easy. That's a radical of the product is product of the radicals, and so that becomes 2 radical 5 by definition of radical. Okay, and that's called simplify. One more time, 45. Now see, we didn't get lucky here. 4 doesn't go into it, but another perfect square does, 9. This would be 9 times 5 by times table, and now you see the square root of 9 is easy. The square root of 9, radical of the product is product of the radicals. Square root of 9 is easy, that's 3. 3 times square root of 5 by definition of radical. And so now we've simplified the radical. Okay, if one of them is positive, you can break it up into little baby pieces. Hopefully one of those is easier. We try to look for perfect squares that go into the number. In this case, for example, I know 100 goes into there by times table, and I know that the square root of 100 is going to be easy. So by radical, the product is product of the radicals, and the reason this is easy because the square root of 100 is 10. I know that because 10 times 10 is 100. I didn't go to school for nothing. There you go, simplify the radical simplified. Alright, the other thing that you should try to remember here, sometimes it might be useful, is you can do the same thing with quotients. You can take the radical of a big fraction and turn it into the fraction of little baby radicals. Radical of the quotient is the quotient of the radicals. Let's see how that would play out. Suppose you have something like this. So you could say, if this is given, and at least one of them is positive, here the 3 is positive and the 4 is positive, so this is legal. Break it up into little baby radicals. Radical of the quotient is quotient of the radicals, and now it becomes easy because the square root of 4 is 2. And so there we go, we simplify that. Let's see if you can see it. You may not be able to see it. Let me see if I can zoom out here. That might be better. Alright, so maybe. Yeah. So there, let's try one more time here. What about 12 and 25? You could say, well, that would be equal to the square root of 12 over the square root of 25. That's by radical of the quotient is equal to the quotient of the radicals. And this one would be equal to the square root of 4 times 3 over the square root of 25, and that would be by times table. I'm writing this because there's no room down, but I'm writing the justifications here. Actually, I like this way of writing justifications. It's novel. Square root of 4, square root of 3 over the square root of 25. Here I broke up this radical into little baby pieces. The rule for that, or the theorem for that is the radical, or the product is the product of the radicals. And now here I get that 2 square root of 3 over 5, and that's by definition of radicals. And there you go. Every single step, perfection. And we haven't proved these theorems, by the way, but it's a fun exercise. You should try to prove them. Prove that the left side is the right side, using the definition of square root, of course. Maybe I should prove that for you. That would cost you extra money. Alright, very nice ideas here. Simplifying radicals. Maybe we try one more. Let's try one with x's. So here I can break this up. The 27 is positive, so I know I can break this up as 20x over the square root of 27. That's the radical, or the quotient is quotient of the radicals. That's how I go from here to here. Here I can break it up as a square root of 4 times 5x. I love 4s. I love 4s and 9s and 16s and 25s and 36s and 49s. And what's after 49? 64s and 81s, because they're all perfect squares. Here I love 9s, the square root of 9 times 3, because that's a perfect square. And this is just times table. And then from here, what can I do? I can break it up into little baby radicals. Square root of 5x, square root of 9, square root of 3. That's because the radical of the product is product of the radicals. And that just becomes 2 times the square root of 5x over 3 times the square root of 3. And that's by definition of radical. And there we go. Another one, simplified. Alright, so we've learned the square root property. We've learned it when the right hand side is not a perfect square. We introduced this brand new idea of square roots. And we learned a little bit about square roots, how to simplify them. I think that's a nice day. I think that's a good day for us. We'll see you guys next time. Peace.